Test next class on Tuesday covers up through the 8.2, so 7.1, whatever we talked about in chapter 7. We've left out part of 7.9 and all of 7.10. What we're going to talk about today, I just want to, let's see, since there's not so many of us here, I think I'll do the easier of the two things of kind of extensions. The remaining sections we have in the class are just kind of extensions beyond what we've already talked about. So it's closely related to what's on your exam and actually can be used. So that's what I'm going to pick today. The stuff that actually can be used to solve what's on your exam, but you just don't need to because we've got right triangles. But if you remember what we talked about last class, we talked about solving right triangles with trig equations, like, you know, sine is opposite over hypotenuse. That kind of combination of things is the same as sine is the y-coordinate over the radius value, that ratio, when we're dealing with angles positioned in standard position in a circle on the xy axes. So in any case, there are other ways that you can solve for pieces of triangles that don't just involve right triangles, but like any sort of triangle. So we'll talk a little bit about that today because you can use these for right triangles also. So could be useful. But then I just want to spend a little bit of time looking over your exam review, see if you have any questions, as long as there's just a small number of us here today. So let's see. Right triangle trig. So your homework from 8.2 is due tonight, the application stuff. Let's take a look at that actually, as long as I've got this right here. I was trying to remember what questions were on this assignment. So some of these have diagrams, some don't. This first one does not. That one has part of a diagram. It shows you what it's talking about with x, y, and theta. Some diagrams, some not. Like I talked about in class on Tuesday, if there's a long description of something where there's either coordinate points or measurements or objects in relation to one another and there isn't a diagram, please draw one for yourself. It'll make your life a lot easier, whether it's on the test or homework or whatever. Helps you kind of put all the pieces together, make sure you're not like changing in your mental picture of it in mid-question. So looking at this first question, which is an example of one that doesn't have a picture associated, it says a rocket's fired from the ground at an angle of 1.06 radians. So that's relative to the ground, or we were talking about a word for that sort of angle, not in terms of like a launch angle, but just a looking at an angle, the angle of elevation, that's an angle up from the ground. This one's more obvious, maybe because of how it has to be mentioned, you're launching at an angle from the ground. It says, suppose the rocket's traveled 460 yards since it was launched, and yours probably has a different number there, but in both of these spots, but the relationship between the pieces is going to be the same. It says, draw a diagram, because it's homework, it gives you a hint, and label the values you know. So if we have the ground and we have a rocket that's launched at an angle to the ground, you imagine, okay, the rocket's going up this way. Whatever the number is that you're given, it's talking about how large this angle is. So mine's 1.06 radians, yours might be something else. But when it mentions that the rocket has traveled so many yards or whatever, I think it's yards in everybody's questions, the distance that the rocket's traveling this way, like diagonally up into the air. So it's talking about the length of this segment at some point in time is 460 in my case. I've seen others with 400 and something else, 300 and something. But in mine, this 440 is talking about this length. At some point in time, it's traveled 440 yards. And I want to know how far it's traveled horizontally and what its height is above the ground at that point in time. So how far it's traveled horizontally, it just means like relative to, like people standing on the ground, how far like left to right in this diagram has it gone, as opposed to how far it's physically traveled, which is going to be farther because it's not only going, it's traveling like it's traveling in 3 dimensions, but it's moving in 2 dimensions. It's going up, but it's going across and up. So this 440 is a combination of things. how far it's traveled horizontally is asking about this. What's its height at that point when it's traveled 440 yards is, asking about the rest of this triangle. So we can formulate a right triangle out of this. If I want to know how far it's traveled horizontally, I'm going to label that x since it's a horizontal distance in my diagram, might as well. If I wanted to put this into a circle, I could make this an angle in standard position. So this is along the x-axis, this would be the radius, and so forth. And so this coordinate point where it hits the edge of the circle, xy, I'm looking for both of those numbers. And this is our, I'll call it theta, just these are standard letters that we've been using for this. I know this x is our cosine of theta, and y is our sine of theta. When we're dealing with circle diagrams, which I made this into, or if you just want to think about, okay, sine and cosine of those. So we're solving for the x and the y. These are useful orders to have them in. But we could also say like r equal, let's see, x over r equals cosine of theta. That's the other way that we normally have these rearranged to have like cosine by itself. So if I wanted to know the cosine of the angle, I'd need to know x and divide it by r. It's the ratio of the horizontal to the ratio, or how many of these there are per that, and it's less than 1 all the time. How many of the vertical per radius there are, that ratio, that's our sine ratio. But in any case, we're trying to solve for x and y, essentially, the horizontal distance and the height. So our cosine of theta and our sine of theta, respectively, will get us that. And we have the r, as long as you realize that diagonal measurement there, relative to the ground and the height, which are perpendicular to one another, corresponds to the hypotenuse. You can just do this as a triangle without a circle involved. And we can talk about this as the adjacent side, and this is the opposite side, and this is the hypotenuse. Just keep in mind this is radians. And whenever you're doing these application problems, a lot of triangles give you angles in degrees, not all of them. This one is one where it doesn't, but just make sure whenever you're pushing on a calculator sine, cosine, tangent buttons or their inverses, that you're aware of what mode your calculator's in. You probably will have to switch back and forth during the course of your test. So make sure you know how to change the mode of your calculator and remember to do it also. So in any case, if I wanted to think about this just in terms of a triangle and I'm trying to find x, I might think of, let's see, x, that's like, this is adjacent and that's hypotenuse, and I think cosine's adjacent over hypotenuse. So cosine of 1.06 is this adjacent side over the hypotenuse. But by the time you solve for x, it's 440 times cosine of 1.06, which is the same as r cosine of theta. It's the same expression regardless of how you think of it. So you can translate things into circles and angles in standard position, or you can leave them as triangles on their own. It's up to you. You get the same answer. It's just a matter of how you prefer to think of it. Better to have more tools than fewer. So in any case, you're going to have different numbers in this, but to find the height, same thing, we're just talking about the sine function instead of the cosine function for that vertical as compared to horizontal motion there that we're trying to measure from this specific freeze point in time. At some point in time, the rocket was 440 yards away from where it started, straight line distance-wise. So let's see. Here we go. One where there's unknown angles. So this antenna has 4 guy wires, these like supporting wires that are making it stand stationary. So it's like kind of anchored to the ground, tethered to the ground. Here's the side view of what we've got. And again, you're going to have different numbers in yours, but I just wanted to go over this like solving for angles piece. Oh wait, no, this gives us this. So, sorry, I'm looking for a different picture. This one where there's, here's, this gonna be, how far? No, I swear there's one with an unknown angle in this. All these give the angles. I must be thinking of another assignment that, all right, well, this one we're solving for angles. So we've got this ladder that's sliding down away from the wall in a kind of weird way, but slow enough so that we can see it instead of just a thump. So we've got a 15-foot long ladder. So the 15 feet, if I'm thinking about a triangle, what aspect of the triangle is the fact that the ladder's 15 feet long going to be? Yeah, it's going to be the hypotenuse. Or if you want to draw it into a circle, it's going to be the radius. It's the R value. It's this diagonal. It's at various shades of diagonal, but it's not perpendicular to something all the time. The Y and the X, the floor and the wall, or the building, are the things that are perpendicular to one another. And this ladder is at a variety of different angles between those two. So the right angle is someplace else, not related to this ladder. So depending on how far away the base is, we're going to have different angles, right? The longer that X gets as it's sliding away, you can see the angle starts large when X is small, and the angle gets smaller as X gets larger. Or if you're thinking about Y is large at the beginning and shrinks the same way that the angle does. So that might also seem familiar, like, okay, so when the Y is small, the angle's small, Y is big, angle's big. Okay, that's the sine function. Our sine function does that. Our sine function starts at 0 when we've got a 0 degree or 0 radian angle and increases as we rotate around until that Y value is at its maximum at 90 degrees or pi over 2 radians. Cosine, on the other hand, starts at its maximum when we have a 0 radian or 0 degree angle. Because it's talking about that x-coordinate, how far to the right of the center of the circle I am, which when you start rotating upwards, you're getting closer to the, not to the center as in the origin, but to that center line of the circle, to the center diameter. You're not to the right of the center anymore when you're straight above it. So the cosine value shrinks as the angle increases. A sine value increases as an angle increases from 0 to 90, and then it goes through, it periodically fluctuates. But in any case, if the base of the ladder is 5 feet from the wall and I wanted to find this theta, base of the ladder is 5 feet from the wall, and I want to find theta. If you want to draw this into standard position, we can do that. We want to think, okay, ladder's this way. The 5 feet is along this way, because our angle is measured between the 5 feet and the ladder. So our angle in standard position, or as a part of a circle, would be more like this. So the ladder length is the hypotenuse, as we talked about. This was what was it? 15 feet in my case. Yours might be a different length. But if I want to know this angle theta here, or here, I've got the hypotenuse of the triangle and the side adjacent to it, or this, corner is what I'm dealing with here. Here I've got the same situation. I've got a hypotenuse, which is the radius of the circle, and the x-coordinate, or the horizontal distance. So this is a cosine relationship that we'd want to know if we're dealing with when x is 5, or when this ladder is 5 feet away from the wall at the base. So cosine of our angle would be 5/15 or 1/3. So remember, that means that to solve, to find our angle, we need to do inverse cosine of, 5/15 or 1/3. And it's a positive number. We talked about last time. If you do inverse trig functions of positive numbers, you're going to get acute angles for any, like, inverse tangent, sine, or cosine of a positive ratio. is going to give you a first quadrant sort of angle, an acute angle. So if that's what you're looking for, great, you're done. If that isn't what you're looking for, you translate into other quadrants, and I was going to talk more about that today, but we'll spend more time on that after your test when there's more people here. So in any case then, that inverse cosine, just make sure, again, if you want an angle in degrees, make sure you're in degree mode when you do that on your calculator. I think this one, let's see, let's say, write a formula that expresses theta in terms of x. So we wanted radian measure for this particular one. But remember for iMath, if you do want a degree answer, you have to put that d in there. But also, this is the kind of like inverse cosine, like inverse functions at f with a -1 notation. But that means the same as arc cosine. Those are two different notations for the same thing. And one is obviously easier to type than the other. That's the one that iMath likes, arc cosine, without all that other stuff in there. I'd do arc cosine of 5/15 for this. Now, if I wanted the answer to come out in degrees as opposed to the answer coming out in radians, because the output for inverse cosine, arc cosine, also inverse sine, inverse tangent, the output from those is an angle measurement. If you want it to come out in degrees and you're working in iMath, put a little d at the end of this. So if I wanted it to be in degrees, I'd put arc cosine d. That's just an iMath thing. You don't have to do a conversion with like pi and 180 degrees or anything like that. Just you can just throw in an extra d at the name of the function and it will deal with it in degrees. That's how you change the mode in iMath. But on your calculator, if you want it in degrees, put yourself in degree mode and you have an inverse cosine button on your calculator. This will come out in degrees, and I don't know how much it is. Let's see, I don't know, like 60 something degrees maybe. But if we just want radians, in radian mode on your calculator, or just type this way into iMath if that's what you want. So to find the value, you do the evaluation. This is they wanted the formula for that second part there. So it's a rather short assignment. Before I leave this, were there any questions while you were working on this that you had? And there's only so many different ways we can set up a right triangle and have unknown pieces. So what I want to look at today then is what if you have triangles that aren't right triangles? Because it's related to what we were talking about, and the techniques we can use to deal with triangles that aren't right triangles, we can also use on right triangles. The law of sines and law of cosines, which comes from, let's see, is it section 8.5? Let me take a look. It's chapter 8. Yeah, 8.5 and 8.6. I was trying to remember if they split this up into two pieces or not. So yeah, 8.5 and 8.6 are about things called the law of sines and the law of cosines. And they look a little bit of a mess. But let me start here's what the law of sines says. And you could also write this. It's a proportion sort of thing, but it's a triangle, so you can set any two of those three pieces equal to one another, as long as you have 3 out of 4 pieces. And you can solve for the fourth one. So if you know like side B and side C and either angle B or angle C, you're good. Or if you know angle B and angle C and one of those two sides are good, or whatever. But just kind of, if you remember this from maybe like high school geometry, standard triangle notation, like capital letters are for the angles and small letters, lowercase letters corresponding to uppercase letters, those are sides and angles that are opposite from one another. So side A is across from angle A, side B is across from angle B, and so on. And the ratios of these are consistent. Not the angle measurement to the side, but the sine of the angle measurement to the sides. It's the same ratio for any pair of corresponding opposite angle and side pair, regardless of what you call A, B, and C. So, but there are 3 of them within the same triangle. They all have the same ratio. A eraser. So there's a lot of different kind of like explanations for why it kind of works, but basically it comes down to, for any non-right triangle, you can make right triangles either out of it or by extending it, and come up with this just by using regular trig. So let me just do a triangle that looks kind of like the one that's up there. Tried not to make it look isosceles, but it does kind of anyway. There, that looks less isosceles. So let's say that this is there's no 90-degree angles in this. So this looks less than 90 degrees, these certainly do. If I draw, and I could have done this from any of the 3 vertices, but what's called an altitude, a line from a vertex that's perpendicular to the side opposite it, I can split this into 2 right triangles. So let me label it with the same letters as this has. I'm going to call this angle A, this angle C, and this angle B. So I've just split side B into 2 parts, and I don't know how long each part is, and I don't really care right now. I'm more concerned about side A and side C. So I have these 2 right triangles. I'm going to call this altitude here, this perpendicular. I'm going to call it H, not for hypotenuse, but it's the height of the triangle. So if I look at the triangle on the left, I have this angle and this side across from it and this hypotenuse of that now right triangle that are labeled. So I'm going to talk about those. This angle, this opposite and hypotenuse, that's related to a sine function. So the sine of angle A in that left triangle that is now a right triangle would be H over C. If I use the triangle on the right and think about, oh, well, in this one I have this angle labeled as angle C, there's this side opposite, and then there's this hypotenuse. A is the hypotenuse of this right half of this triangle. So I could say that the sine of angle C is H over A. So I have 2 different expressions I could write for H rather, and they've got to be equivalent, right? If I rearrange this and solve for H, it'd say H equals C sine of A. So little c, meaning the length of side C, times the sine of angle A. And in the other equation, this one here, if I multiply both sides by A, I have H equals side A times the sine of angle C. So since this is the exact same H both cases, these 2 have to be equal to one another. C sine of A is the same as A sine of C, which is confusing to say. Get a bigger piece of chalk here. But since those have to be the same, let me write that smaller. C times the sine of angle A has to equal side A's length times the sine of angle C. Or if I turn this back into a proportion, you can do it either way. I'm going to divide both sides by the sines, like divide both sides by sine of A and by sine of C. I can do it one at a time, but I'll do them both at the same time. Divide by sine A, sine C. If I do that, I have side C over sine of angle C and side A over sine of angle A that have to be equal. Or in other words, I just took this, nice sort of looking thing and turned it into a proportion. So the proportion is not a solved form of an equation, but it's succinct, it's compact. So, but the point is, and I could have done that by drawing, I just drew this because it was vertical, so easy to see a perpendicular line. I could have drawn instead a line that went this way and was perpendicular to that side and done the same sort of thing. I would have come up with a different combination for those, but regardless of which pair you end up with, you can do that for any pair of two, and so it actually works for all three angles. And oh, also in this, from this, setting these equal, I could have, instead of dividing by the sine functions, I could have divided by the a's and the c's and ended up with those on the bottom instead. It's just a proportion. Like if I have 1/2 equals 2/4, that means 2/1 equals 4/2. You can flip the pieces of proportions if you like them the other way also. This is just one way to write this. But the pieces of this are all equal, whether it's a right triangle or not a right triangle. We don't really talk about solving for like using the sine of 90 degrees. Well, it's 0. Or sine of 90 degrees is 1. Sorry, I was thinking of cosines all of a sudden. Sine of 90 degrees is 1, and so we don't have to deal with that so much. But you can use this to solve for pieces of non-right triangles. So let me just pull this out. There's a whole little blurb up there. In order to be able to pick two pieces and solve, like I said, you have to have, like let me just say we have A's and B's. Like, you have to have 3 pieces of information, 2 angles and a side, 2 sides and an angle. Having just 3 sides, you would not be able to pair up any of these and have 3 out of 4 known to solve for the 4th. So it's got to be like 2 sides and an angle or 2 angles and a side. But they also have to involve one opposite pair, like a side and angle pair, because you have to have 3 out of 4 of those. One of them has to be like, one of those is a full fraction, top and bottom are both numbers that we know. So you have to have an angle and a side that are opposite from one another. So if you know all 3 sides, we're going to use the other rule, law of cosines. Thinking about like stuff that you learned in geometry about proving triangles congruent, that doesn't seem like it's really related here, but if you know you have congruent triangles, that means you know exactly what shape and size a triangle is by having this certain combination of information. So if like angle, side angle, if that sounds familiar, like weird geometry proofs in like 9th grade, 10th grade, whenever you might have done this. So that sort of, if you have that combination, like that arrangement of pieces in a triangle, you'll be able to solve for it because that determines one specific triangle. Side angle is not a geometry theorem. Because there's, depending on what you have and how long the pieces are, how long the sides are, which the longer ones next to the angle or across from the angle, sometimes there's more than one triangle. That we're going to talk about after your test, just briefly. But other than that, and you're not going to run into those cases here, other than that, you can use these to solve for missing parts of a triangle. So let me just open up this law of sines homework. So this first question kind of talks through what we just went on the board. But let's look at, this is like question 3. This is my version of it. This has angles measured in degrees. So just be aware of whether it's degrees or radians. This one happens to be degrees. But it says we have angle A. That bottom left corner is 54 degrees. The side next to it is 7.5 centimeters, and then the side across from it is 19 centimeters. This is this side angle sort of arrangement. The angle's not between the 2 sides, it's off to the edge. But that's okay. We have an opposite side and angle pair. And this one is not set up to be a weird case with ambiguities involved. The ambiguities come into play here because of the fact that inverse sine, sine values are positive for both acute and obtuse angles that can fit in a triangle, like under 90 degrees and over 90 degrees angles in a triangle can have the same sine values. So if you don't know quite how things are arranged very well, you could end up with having an acute or an obtuse angle in certain positions, but not in this case because of where the sides are. We've got too long of a side across from this 54-degree angle. So in any case in here, That's angle A and side A, or those two would be in a fraction together. Sine of 54 degrees and 19 centimeters. I could use that along with 7.5 centimeters and solve for the length of this bottom side. Or not the bottom side, bottom angle, angle C here. So this would be side C, it's across from angle C. So I should be able to solve for angle C by setting up a proportion here. I could also solve for angle B if I wanted to, and you can solve for them in whatever order. Let's see, this one. In terms of what we know. And when it's just generic A, B, C sort of stuff, I think sometimes it's kind of useful just to write it out in a list, what you have instead of on the diagram, like, all right, angle A, angle B, angle C, side A, side B, side C. What do we know? Angle A, in mine at least, 54 degrees. I don't know the other two angles. They're not listed in the text and they're not in the diagram either. So this would be side A, that's marked as 19 centimeters. And then side C, since it's across from angle C, that's that 7.5 centimeters. So using law of sines, easiest bit to solve for would be that one, because I can use a proportion with the A's and the C's. And you can do it either order. I'll write it the opposite order from how it was on that sheet. There's the angles on top. Sine of A over side A, and sine of angle C over the length of side C. These should be equal, according to the law of sines. So that's sine of 54 divided by 19 should be the same as sine of angle C over 7.5. And so to solve, cross multiply, and then divide by 19. So I'd get this sine times that equals 19 times sine of C. So I'll write this 7.5 sine of 54 degrees equals 19 times the sine of C. And we're going to want C in degrees, so just keep that in mind as you're working through this. But to solve then, do a divide by 19, and then that's that fraction or weird decimal you get is going to be the sine value for angle C. So to get C, the angle, I'm going to do arc sine of all of that. And in iMath, if you want to write it as an expression, arc sine D to get it to come out in degrees. But that's angle C. My question here asks for angle B and side AC, the length of that segment, which would be side B. So you can name segments by this triangle method or also by their endpoints. So we can't get either of those directly because we don't have either one to find the other. But now that we have angle C, which I don't know what that is off the top of my head. Anyway, what does this come out to for angle C? It should be a smallish angle. Arc sine of 7.5, sine of 54 divided by 19. Let's see if it'll do this. That's going to be radians. Let's see. Arc sine of 7 point sine. No, that's not liking me because it wants the 54 to be in radians. So I'd have to find a different online calculator to do this. But let me just say, as an example, it's a smallish angle. So where'd we go? So let me just say that it came out to be like 19 degrees, just to have it be something. I don't know what it is. So let's say it came out to be 19 degrees. We still don't have angle B or side B, but we actually know angle B at this point. because triangles, 180 degrees should be the sum of the three angles of a triangle, and we just found the second angle. So now we have two angles, and I just made up this 19. But if we have 54 and 19 degrees, oh, I shouldn't have made up 19 because then it matches that side length. Let me call it 21. There we go. Let's say we have 21 and 54. That makes, what is that, 75 degrees so far? So the rest of the 180 is that other angle. So it'd be 105, right? Did I say 75 or did I say 85? 75, yeah. So 105 degrees for the third angle. And then we can use that to find the third side. And when you're looking at these, when you have all three angles, it should be in sequence, like the smallest angles across from the smallest side, and the largest angles across from the largest side, and the mediumest angles across from the mediumest side. But in any case, once we have those all, and this isn't drawn completely like, not drawn to scale, don't try to use like a protractor or anything to measure the angles. We're going to solve for them, but it's not drawn to be completely misleading. It's just it might not be precise. So everybody's got the same diagram, and some slightly different angles for that angle A are going to be given in your homework assignment. But in any case, if you can solve for one piece, after that you have two side and angle pairs. You can always find the third angle after that by subtracting from 180 degrees, or if it happens to be labeled in radians, subtracting from pi radians, right? Because pi radians is the same as 180 degrees. Don't normally think of like the angles of a triangle adding up to pi, but that would be true if we're working in radians. So in this triangle here, this is just the next problem. Note that two of the angles are already given. So if you want to just write in the third angle, we already know that because these add up to, oh, let's see, what do we have? Can I add? 81.8 degrees so far. So we have just under 100 degrees for the third angle that isn't labeled. So pretty similar in shape to the previous triangle. One angle that's just over 100 degrees and then two other angles. But in any case, solving for the lengths of those other two sides, you could, other than the one that's listed, you can do that by using, well, to find the side C that's on the left there, across from angle C, you can use just the information that's literally already in here. We've got angle A and side A. We can use angle C and solve for the side across from it. And solving for sides doesn't involve inverse trig functions. Only solving for angles does. So there's no weird ambiguous, how do I do this, or am I in degrees or radians that I have to worry about. Everything's already given in degrees. Just make sure you're in that mode and your sides will come out properly. But you will have to find angle B just by subtracting from 180, which is like just under 100. Whatever I said, that came out to 81.8. So we have, what, 98.2 for that third angle. So let's take a look at law of cosines. Actually, let's take a look at this, how this would play out if we accidentally started to use this on a right triangle, because it doesn't cause any problems. I just wanted to point that out. If you happen to have something that's a right triangle and you're using law of sines, you don't like get wrong answers. It still works. So let me just draw it like this way, and there's A, B, C. I'm going to say, let's say angle A, angle B is 90 degrees. Not marked as a right angle, but it's 90, and we can go through solving for the pieces anyway. And angle C, let's say that I have, this side is 14, and this angle is, what does that look like? 60, no, I'm not making it nice and even, 55 degrees. So angle A is 55 degrees. So I know what angle C is. It would be, what, 35 degrees? The side opposite from angle A, we don't know. The side opposite from angle B, or the side opposite from angle B is 14. side opposite from angle C? We don't know. But since we have this information, whether or not you think, oh, that's a right triangle, let me just use like sine is opposite and hypotenuse and that sort of stuff. You can still use the law of sines, it still works. So we can use the A's and B's. We can set up and do something like, all right, sine of angle A over side A, the thing I'm trying to solve for, is the same as sine of angle B, which is 90, over side B, which is 14. So I'd get sine of 55 times 14 equals A times the sine of 90. We just move that. Lowercase a times the sine of 90 degrees. Now if you put this in a calculator, like kind of separately, you might see sine of 90 is 1. So this would come out to be the same as A is 14 sine of 55, whatever that is, which if you think about this as a right triangle, this is the hypotenuse, this, and side A is this one. So I've got the hypotenuse and what do we have? Sine of 55, opposite and hypotenuse. Sine of 55 should be A over 14. If I'm thinking right triangles, that's the same thing, 14 sine of 55. But even if you just punch this in and said, okay, 14 sine of 55 divided by sine of 90, doesn't give you a different answer because sine of 90 is just 1. So it still works. This works on all shapes of triangles, not just non-right triangles. It's just if you have right triangles, you have other, maybe simpler or less confusing rules to use. All right, but let's take a look at law of cosines. Law of cosines, and I'll post this kind of summary document on Canvas as well. But the law of cosines looks kind of like Pythagorean theorem, just with some extra pieces involved. But there's 3 versions, and the 3 versions, you don't need to have all 3 of them. You just need to have one, because you can label triangles however you want. But it's just, here, I'll look at the bottom one, because A is closest, and B looks most like Pythagorean theorem. C squared equals A squared plus B squared, just minus a little bit to adjust for the fact that we're not really dealing with a right triangle. So how the formula comes about is a little bit more complex than law of sines, but it's the same sort of, if I divided this into pieces but didn't know, the right pieces to use sine functions, if I needed to use cosine functions instead, we can set this up and talk about solving. Now, this is going to be useful. Notice all 3 side lengths appear in this. 2 of them show up twice, so like side C, side A, side B, side A and B again, and 1 angle. So this is useful if you know a lot of sides of the triangle. If you know all 3 sides, like side, 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 geometry stuff, you can solve for the angles, any of them with this. If you know 2 sides and an angle, but it's not the 2 sides, like there's not an angle across from a side, like side angle side, sort of like, like one corner of a triangle, where if you try to use law of sines, none of them are opposite from one another, like side A and B along with angle C. You can't use the law of sines for that because there's no full proportion fraction that you can, there's no set of 4 parts that fall into 2 of those fractions. So it looks messier. And by the way, these will be listed for you on your final exam. You don't have to have these memorized. You just have to generally know what to do with them. But like I said, these are, the 3 different versions are just, from the perspective of different sides. And since it's not, there's one right angle and the others are non-right angles and acute, any 3 of these could be, these all mean the same thing. These 3 versions are just from the perspective of different angles. And so if you had a triangle labeled as A, B, and C, you can just pick the one that matches what you need. But for instance, and let me pull up the iMath homework on this section. which I have these due next Thursday, a week from today. But looking at, and let's see if I make this a little bit bigger. This question was just asking on which of these would the law of cosines be helpful? So law of cosines is generally helpful if law of sines isn't. But if you have all three sides, like I mentioned, you can use the law of cosines. If you have nothing that's across from one another, like angle A and side A, you can use it. So this is labeled, I don't know, top triangle, this triangle, those would both be useful. This one, because there's no like angle across from the side. Let's see, and I think that's it. So the top one, this one, that one. The rest of these all have at least an angle across from the side. And so if you tried to fit them into this, we don't have the right pieces. Notice that these have an angle, the side that shows up once is across from the angle that shows up on the other side of the equation. So angle C and side C are both going to be in one version of this, regardless of which one we're looking at. But there are two sides that show up a bunch of times. You can't solve for like any part that you want. You have to solve for, you'll be able to solve for a specific part. Let me show you what I mean by that, because that's just confusing to say. Let me just do this one. This is that like side angle side. There's no side and angle that are across from one another in this triangle. So this is labeled with, we have angle C, and so those would be sides A and B since side C is across the triangle. But in terms of looking at that format, we want to pick the one that has the angle C in it, which starts with side C squared, A squared and B squared, minus 2AB cosine of C. So like I said, it's kind of like Pythagorean theorem, but just with a little adjustment for the fact that we don't necessarily have a right triangle. If you do, by the way, have a right triangle, and C is the hypotenuse, and this is the legs of the right triangle, the cosine of angle C, if side C is the hypotenuse, then angle C is the right angle. Cosine of a right angle, cosine of 90 degrees, is 0. And so that term drops off, and you do have exactly the Pythagorean theorem. So it does work on right triangles also, just that that whole adjustment turns into a minus 0 at the end. So if I use this law of cosines with that triangle there, I just wrote this version because it's labeled as angle C, so I'll use that. All I have to do is fill in the blanks, and you'll see that those are A and B that I don't know. The part of it that I don't know is this angle, this side C. So C squared would be the other two sides squared, 14.5, not nice numbers, and 28.7. Just in terms of typing this in a calculator, realize that all of this is subtracted. So this whole expression here, 2 times 14.5 times 28.7 times the cosine of, what was it, 21.8 degrees. So make sure you're in degree mode. And if you're calculating this out kind of piece by piece, realize that this whole extra term is subtracted. If you have an obtuse angle here, something more than 90 degrees, something more than pi over 2 radians, realize that the cosine of that is going to be something negative, because it's talking about your x-coordinate relative to around a circle. So it could be the fact that you end up actually adding if you're subtracting a negative. Your side lengths are going to be positive, but it's possible that this cosine is actually negative in value if you have a large angle, an obtuse angle. If you don't know the size of the angle, well, you can find that out. But in any case, notice that this is then just, oh, this whole right side is a bunch of numbers. It's definitely very calculatory, so I don't want to spend a lot of time on it. It's just punch a bunch of stuff in a calculator. That's C squared. So then take the square root, and you should get the length of side C. So that's the case of solving for a side. Once we have that other side, whatever this turns out to be, and it's a small angle, so it should have a relatively small side across from it, maybe like 12 or 13 or something. I don't know. Maybe it's bigger than side A, so maybe it's got a like 16 or 17-inch side across from it. But once we have that, then we have an opposite side angle pair, and then we don't have to use law of cosines ever again. You only ever have to use law of cosines once in a triangle. Once you do, then you definitely have an opposite side angle pair. And you'll be able to solve for anything else that you might need, either using like subtract from 180 to get the remaining angle, or use the law of sines to get a remaining side that's left over. You can use law of cosines again if you want to, but the things that you'll be able to solve for are either going to be that side that's by itself or this angle. The other things show up too many times to solve for them, so you're either going to solve for that one that's on the left by itself by subbing in a whole bunch of numbers and taking a square root, or solve for the angle by subbing in all these numbers and doing a lot of subtracting, and then divide by this negative here and an inverse cosine. A little bit messier, but we'll see each other again next Thursday before this homework is due. I think there's only, just one of these. If you have all three sides and you have to solve for an angle, doesn't matter whether you call it angle A, B, or C, you'd have to use inverse cosine to solve one of those. And you can pick whichever whichever side or whichever angle you want to solve for first. Go for it, doesn't matter. But you're going to have to use an inverse cosine in order to get an angle result. So let's talk about test stuff then. Let me go back to main page here. So, there are a ton of questions on here. I did want to point out at the end, where does this start? There's some things at the end, right after this. Questions 40 onward, not needed for exam 3. This is examples of, solving non-right triangles, stuff we were just talking about. So I've got these random degrees. This is not going to turn out to be 90 degrees, but I should be able to solve for any of the pieces in that triangle that I need. Same, solving non-right triangles, same, solving non-right triangles, solving non-right triangles. So you see that's a lot of what's left in the class. We will talk about this question 45. This is that idea of that ambiguous law of sines usage. If you happen to have two sides and an angle, not the one in between them, but the one off to the side of them, and the shorter ones across from the angle, like this, so the shorter of the two sides is farther away from the angle, it's possible that there's two different positions I could put that third side in. Since I don't know how long this bottom side is, I don't know how long that angle between the two sides is, I could arrange it two different ways, like swinging a pendulum, where it fits both ways. And the reason that happens is because, here's an acute angle. It has a specific sine value. The upper picture there, the angle between the blue and the dotted line, is obtuse, and it has the exact same sine value as this acute angle does. Because first and second quadrant angles can have the same sine values. So sometimes there's two different ways. It's only in this weird specific, and so this is one example of that. Hint, there's not going to be one on your final, but I did want to point out, just to not leave anything out entirely, that it's possible to get two different triangles from given information if all you have is the specific, like one angle and then two sides off to the edge of it. The last other thing that we're going to talk about after your test is just some fussing around with, since sine and cosine are related to one another, they're about y's and x's, and think about like y's and x's and hypotenuses and triangles. You can do a lot of like algebraic manipulations to turn one into the other and to relate things, and we're going to talk about these a little bit, not a whole lot, but I'm going to give you a list of facts. I'm actually going to hand that out when you hand in your test on Thursday, and we're going to talk about those, when you hand in your test on Tuesday, and we're going to talk about those on Thursday. Just some what are called trig identities, just some facts about how trig functions are related, including, you'll see there are some other things, not sine, cosine, and tangent, COT, cotangent, that's the reciprocal of tangent. Where's another one? CSC, cosecant, that's the reciprocal of sine. So, well, if cosecant and sine are reciprocals, if I multiply them together, I get 1 all the time. Same with, that was a sine and a cotangent. But I'll have just a sheet of a few facts, and these will also be facts that you'll have for the final. And it's just some common substitutions that people make in order to change one expression into some others. Honestly, people try to avoid writing anything in terms of cotangent, cosecant, and secant. The only reason they do is to make it look shorter, but those functions are rather unpleasant to deal with. So the end is just manipulating trig functions and not actually solving for new information, but just like rewriting in different forms. And so that's what the whole last part of this is, after, like from number 40 onward. But stuff that is on your test goes from the very beginning. We talked about how do you even measure angles? What does it mean to measure an angle? It's all relative to something, right? Like 0 degrees, 0 radians are the same, but I have to like pick a unit and say, okay, so there's going to be 360 of these make a full loop around a circle. Okay, so that means that if I go a quarter of the way around the circle, that's a quarter of 360. Or if I say there are 10 of these to go around a circle, whatever it might be, then, well, if I want to go halfway around, that's 5. So it's all relative measurements when we talked about degrees and radians and how those were set up. And then we talked about the arc length, and radians are the unit of measure for angles, so that the number of radius lengths you've traveled around a circle matches the angle measure in radians. So if you've traveled 1 radius length around a circle, then that means you've traveled 1 radian in angular measurement, measuring in radians. So the arc length is the same as the angle measurement when we measure in radius lengths. But if you want to convert into like feet or kilometers or normal distance units instead of radius lengths as units, just multiply by whatever that radius length is. So it would be one of our 3 common things that I kept writing. Our arc length is just our radius length times our angle measurement, as long as we're measuring our angle in radians. The other 2 things being, they're still up there. X is our cosine theta, Y is our sine theta. All right, so this first bunch of questions are all just about measuring positions around a circle. Sometimes we know the radius and coordinate points. We're finding a missing coordinate point, or solving for the angle. That all came later. But did you have any questions on the first couple pages from the review? This is page 1, and then page 2 has a specific diagram. Anything's? All right, so at the bottom of page 2, it's talking about converting between degrees and radians. So that converting is just using the idea of proportionality again, or that degrees and radians all measure like something relative to something else. So just keep it, there are a variety of ways you can do these, but if I wanted to do something like convert 140 degrees to radians, I can think about how degrees and radians are set up just in order to think to myself how this is done. Well, 140 degrees is a certain portion of 360 degrees. The number of radians that I want to say is equivalent would be the same proportion out of, let's see, well, 2 pi radians is all the way around a circle. And so I could, solve for the number of radians by solving that proportion. I don't have to use 360, I could use anything that's equivalent. Like, I can think, 90 degrees is a square corner. So I'm going to say, how much is 140 relative to 90 relative to a square corner? It's like 1.5-ish, a little bit more than 1.5 corners. I just have to use the equivalent in radians, which is not too pleasant, but you can use any relative measurement that you want to set up these proportions, and they'll all come out to be the same result in the end. You just, if you want it not as a decimal, just you might have to fuss around with fractions. But if you did this, let me just use this unpleasant looking thing. Cross multiply to solve. I get 90x is 140 times pi over 2, which is 70 pi. So no fractions anymore, other than to solve for x, I need to divide by 90. Well, reduced form, 7/9 pi, or 7 pi over 9, whether I want to put that pi on the top or off to the side. Just kind of reducing. Let's see. Definitions of sine and cosine. Sine was designated as the vertical measurement when we're talking about rotations. So our vertical motion or our vertical distance relative to the center, so relative to the x-axis, how high or low are we, or the y-coordinate aspect. But in terms of how we compute that, y is how far it is, not measured in radius lengths, but in like feet or kilometers or millimeters or whatever. R times the cosine of theta, the circle's radius times the, or I said cosine because I'm looking at this, r times the sine of theta, where r is whatever the radius of that circle is that we're moving around. Same sort of thing for cosine. Just trying to read through this quickly. Keeping in mind where these trig functions are positive versus negative. We talked about that a little bit last class relative to, we were solving equations last time. But just keeping in mind like sine and cosine, where they're positive, where they're negative. You can think about their wave graphs to think about that, or think about rotating around the circle where x is positive and negative, where y is positive and negative. Tangent is the relationship in a right triangle between the two legs of the right triangle, the perpendicular pieces. If we're talking about circle and circular motion, it's the y and the x, rise over run. It's the slope of that terminal ray. So where's slope positive? First and third quadrants, second and fourth quadrants, it's negative. So for lines that go through the origin. But that's our angles in standard position. So we talked about symmetry and how there's going to be multiple points around a circle where we have the exact same sine value, but then their cosines would be opposite, or exact same cosine value, but then their sines would be opposites, or the exact same tangent values. But those are all just based on symmetry, coordinate points, how those are related to the sine, cosine, and tangent values. Let's see. Suppose I wanted to, this is a weird looking question, so let's take a look at this. Which of the following choices could represent the coordinates of the point at the end of the terminal ray of the given angle theta? So theta is 3.92. This is measured in radians. I can tell because that's certainly not 3.92 degrees. I can see that the radius of this circle is 2, right? Because it goes from 0, 0 to 2, 0. So I've got a circle with a radius of 2, and I've got an angle that's 3.92 radians. If I want to know the coordinate points here, r cosine theta, comma, r sine theta, right? So it's just this last option here, but take a look at what these others have or are missing. So we don't need to put in negative signs. There's some negatives in some of these answers. Those come out automatically. It does have negative x and y coordinates, but when you do cosine of and sine of 3.92 radians, they're both going to come out negative already. So you don't have to insert negative signs to make them that way. You can punch it into a calculator in radian mode and see that you'll get some negative coordinates, some third quadrant coordinates. Some of these E and F have arc cosine mentioned. That's inverse cosine. If you tried to type in these expressions, it would tell you error for any of those, because the input is supposed to be a cosine ratio, like a adjacent over hypotenuse or an x coordinate over the radius, and that can't come out to be more than 1. So input to arc cosine, arc sine functions, those are always going to be something between -1 and 1. Arctangent can take whatever, because slopes can be anything. But the ratio between a leg of a triangle and the hypotenuse of a triangle in that order is always going to be something less than 1. If we're talking about not specifically right triangles, but something related in a different quadrant, we could have some negatives involved, but it can't be something that's absolute value is more than 1. So these wouldn't make any sense if you try to type them in, they'd give you errors. It's probably say like error domain. But cosine and sine with a radius of 2 to give us the scaled up factor, because we're not talking about how many radius lengths we are down in that direction, we're talking about how far, what's our coordinate point location. And we have a coordinate point of 2, 0 here. So, oh, this is radius of 2, so twice as large as a radius of 1, or it's not 1 radius length, that's 2, it's 2 units. So this multiplier factor of 2 is what makes G the correct answer for that, and not the others. We just did some solving right triangles, but that's what number 20 is about. You can see like tree growing perpendicular to the ground, flagpole, shadow. The tip of the shadow would be where it goes through the sun rays to the ground, so it depends on the angle of the sun. We've got ships, we've got more right angles. Let's see. Make sure you take a look at 23. We only have a few minutes left here, but this 23, consider the angle shown in the diagram with terminal point located h radii to the right of the vertex and v radii above the vertex. So that's h for horizontal and v for vertical, in case you were wondering about that. If you want to call them x and y, you certainly can, but we didn't want to, the reason they use that is because this way it's not how many units is it, we're measuring in radii or radius lengths. So we wanted for this one inverse cosine of h. So h is a number of radii, or it's also then, since the radius is 1 radii, the radius length is 1 radius length. H is h radius length, which is something less than 1, you can see. So if I were measuring this in like regular units, whatever that radius is, I could calculate the length of h by saying, oh, well, if the radius is 5, then it's 5 times h. But it'd be something less than 5. So h is something less than 1. It's already that fraction, or in fact, h is already the cosine value. Thinking about these, my radius is 1. I'm measuring in radius lengths. So my horizontal measurement is just going to be cosine, and my vertical is just going to be sine, since we're measuring in radius lengths here. So inverse cosine of h, this is, let's see, it's kind of a weird thing. It's like, well, like inverse cosine of something, it's supposed to be inverse cosine of this ratio, inverse cosine of some sort of ratio, but this is a ratio. It's the horizontal over the hypotenuse, which is, or the radius, which is 1 in this case. So inverse cosine of this ratio should give us that angle theta, right? It's a little bit weirdly worded, but just think about these and think about how they relate. It's just that we're measuring this in radius lengths and we're measuring this in radius lengths instead of units. Instead of like inches or like x is 1, 2, 3, 4, because it doesn't tell us what the radius is. But if you want to make a radius length and then make h time, like let's say the radius is 7, then that horizontal is 7 times h, and h is something less than 1. I can't tell what it is, but it'd be, so it's going to be 7 times h, or the vertical is going to be v times 7 times v. You can make up numbers if you want, but just realize that this v and h are going to be something that's less than 1, because those are certainly smaller than the radius. Let's see, other things on here. Oh, calculating sine and cosine values based on a diagram. This one has actual numbers in it instead of V's and H's, so I hope that one's easier to look at. Which trig function takes the input as a horizontal distance and an output as an angle measure? Well, that's exactly what we just talked about. That's that h, but measured in radians, and the output is an angle measure. That would be inverse cosine. So weirdly worded, but if you can draw a picture of it, that can help. Slope of a terminal ray, slope is tangent, right? But our tangent function here, since it'd be like y over x, but that's also sine of 5 over cosine of 5. So sine over 5 and sine of 5 over cosine of 5 and tangent of 5 are both the same thing, because tangent's supposed to be this like y over x, but I know what y and x are here, so I can also, instead of saying tangent of 5, I can also say sine of 5 over cosine of 5, same thing. What's the value of alpha? Can use inverse trig with these functions here. I'd say use the inverse trig on the positive one. I said try to avoid doing inverse trig on negative things. It just makes your life more difficult than you need to. If you do inverse trig on a positive thing, it'll give you a first quadrant angle, but then we can figure out where it's supposed to go. You can also guess and check. Let's see. Quadrants where sine, cosine, and tangent are positive versus negative. It's based on x and y coordinates, right? I think we've talked about all of these fairly recently. Two angles that have the same sine or cosine value, how they're going to look relative to one another, what coordinate points they're going to go through relative to one another. If you know one, you know the other. So make sure you look through the review document. If you have questions, post it in the forum or message me. But the solutions are also posted. They are right here. I just posted those on Tuesday. But the final exam is going to cover not much more new material, just a little tiny bit. I'm going to give you, I'll post it. I'll post the additional material, the trig identities stuff, sometime between now and your exam. I'll hand you out a copy of what it's going to be in class when you hand in your exam next Tuesday. But exam next Tuesday, make sure you come with an ID, a pencil, and your brain fully functional and awake. And we'll take our exam, and that's all we're doing that day. It's going to be 50 minutes like the other ones, 21 questions like the other ones, all multiple choice. So no surprises. Make sure you bring your calculator and that you know how to switch between radian and degree mode, because that is important. All right, that's it. Have a great weekend.